Good morning again, everyone, and really thank you, Greg, for the introduction. But also, this is probably why he's putting me to task to have me talk to you about this so-called epigenetics. And that doesn't even sound like English, does it? Okay, so we're going to actually use very little slides, and we're just going to talk a story of what really is epigenetic. And there's no quiz at the end, I promise. Okay. So far, what you have heard was mostly about the genes, right? The DNA, and how that is the kind of playbook for the eventual functional unit of anything in the body, and that's protein. So you go from the DNA to RNA and then to the protein. Well, but as it turned out, guess what? Over 90-some% of our DNA isn't even sending out the messages in any way in any proteins. Majority of the DNA is actually all tied in together in these little bundles that Dr. Callender showed you earlier in the day. They're actually just kind of all wound up. But when I think about, so what does that really mean if you have 100% resource, but you only use 2%? So what controls that 2% then? So, when I think about that, the DNA library, it's like you look at music catalog. Could be thousands and thousands and thousands of songs, right? So it takes the DJ to pick just what songs you're going to put together in your playlist. So that then make us all, in a way, different in what our cells are doing, in who we are. If you think about what Dr. Callender showed earlier in the genetic composition of cells, she showed you the DNA that really is present in every cell in the body. You can do the buccal swab for the DNA. That's your signature. You can scrape the skin under the nail, or you can really collect my inside cell, and they'll have that same DNA, but all of those cells function differently in different organs, right? What makes the liver cell liver? What makes the blood cell blood cell? It's actually epigenetic. It's actually your DJ that pull out just the right song for that for the function of those cells. So it's actually simpler than one thought then, right? So we're talking about, so what are the DJs? What do the DJs really pull to make myeloma cells myeloma? And when we talk about epigenetics, it's not just in the myeloma cells, it's also how about other cells in the body? Whenever myeloma cells are allowed to proliferate and to grow, are there epigenetic changes that occur in other cells around that control the behavior of the myeloma cells? And how about other cells in the body that respond to medications? There may be also some epigenetic component to that. So I'm going to talk mostly about this field that looks at the changes in the organism by way of modifying what group of genes get transcribed into the protein for the function. So the DJ is actually these little knobs, that are actually bound on to a particular DNA, and that controls whether it will be opened for business. So you actually have transcription of the DNA into the eventually making protein, but there are also some that actually control the tightness of these little bundles. So the genes are there, but if your DJ is actually not coming to work, and that bundle doesn't get opened up, things don't get transcribed. That's actually one of the ways the cancer cells decide to silence what's slowing them down, so then they can just take off. So this is actually an interesting field because it's actually these DJs that control not random mutation one gene at a time, but a whole group of genes that actually are in the play, right? Say, if I have this bundle and I want to turn it on, and it would actually open up this whole segment of the genes. And then all of a sudden you have not just one gene, you have a whole slew of genes that are actually getting to work. But if you actually tighten up this bundle, you actually lose function of not just one gene, but the whole thing that get to be kind of inside the rope, and then you can't just get the protein expressed from the genes that are actually not accessible. All right, so this goes back to the story that is really the holy grail, not just for cancer, but really any other cells in the body. So it's a problem, nature or nurture? And I'm trying to convince you that it's probably both. So you already heard about the genetic mutation. That is really the change within the DNA. It will not change. The cancer cells, when it acquired mutation, it's there. But there's actually this second wheel, right? The epigenetic, the things that are potentially reversible, that's controlling the regulation of the cell through other ways. And some of these are actually reversible. So it's actually worth talking about. Okay. So what then can modulate this so-called epigenetics? What can affect the way cells choose to transcribe certain set of genes? There are many. The unfortunate thing is I don't have a solution today for what you will go home to do that will modify all of these different aspects. But I think that is really knowledge that we're gaining each and every day, right? We want to know what may us all different, but also what can we do that will increase the chance of success in cancer therapy. The genetic mutations themselves, we can't change. Once they're there, and we're learning about how they may affect the cells. But these other aspects, the diet, the exposure to diseases, the toxic chemicals, drug abuse, exercise, there's a whole field of this microbiome. The flora in the gut, it's interesting that it's sort of in the gut, but it's actually affecting the whole immune system in the whole being, including how our body control cancer, recognize things that don't belong to us, and also responds to treatment. There are as the whole aspects of alternative medicine that's probably coming into play in the epigenetic. Even social interaction, people believe that having excessive stress actually alter the way the white blood cell respond to injuries and the way they repair. So I'm hoping to be talking about something that we don't know as much, and may actually end up being an area that's really exploding with all kinds of choices that's available to our patients in the future. All right, so the reason that epigenetics is important, you should at least hear this term, is it always bothers me the most when my patients get diagnosed with myeloma or even plasma cell disorder, the so-called MGUS, or smoldering multiple myeloma. So what caused it? How long might they have it? And so there's got to be an explanation for why this just happened. To call it a genetic accident alone just doesn't make entire sense, right? So there are probably some proof of principle data out there to say that it may be a combination between what we were born with, but also what we're exposed to. And let me show you some of these data on what we're exposed to that may contribute to myeloma. There are not many things in life that there's a predefined time for exposure. There's a before and after. And an example of something like that would be Agent Orange exposure. We know that these veterans at young age got exposed to high dose of pesticides. The Agent Orange has mixture of chemical compounds in there. The primary one is something called dioxin, which is also a pesticide that now has come to light that it does cause DNA damage and lead to cancer. So, but not only Agent Orange, right? So these are our veterans that served mostly in Vietnam War. What became clear was that through their lifetime, there's increase in incidence of multiple cancers, one of which is multiple myeloma, but also got more veterans with burn pit exhaust exposure. There's also increased risk of multiple myeloma. You've heard in the news, particularly if you ever turn on the TV after midnight, you guys, like as many of my patients do, because we give them dexamethasone and they don't sleep very much. So post midnight, I'll get some emails that's asking me questions about this. I can't suggest whether to pursue a lawsuit. I will not do that. But I can highlight that there is increased risk of multiple myeloma among veterans who serve at the Camp Lejeune due to water presumed water contamination, right? And we know that radiation exposure, such as in the nuclear power plant leak, also increased risk of multiple myeloma. So it seemed that multiple things that one might have had exposure to could lead to the same eventual diagnosis of this multiple myeloma, but also it does increase risk of other cancers as well, as you can see. Of course, most of our myeloma patients actually weren't exposed to Agent Orange, but this is sort of a highlight that perhaps there's something in the environment that contribute to the development of the tumors. A more recent exposure type data comes from our firefighters who serve ground zero. They, the exposure to the dust there actually end up, you think, well, it goes into the lungs. Why would it actually do something that eventually causes blood cancer? Apparently, there's just all kinds of changes in the immune microenvironment, in the immune profile, that these young firefighters kind of continue to suffer the consequence through the lifetime. And among many cancers that have actually been diagnosed to be increasing in incidence, myeloma is one of them too. But also, not only there's more myeloma, it also occurs at a younger age. And from the time of exposure to diagnosis of myeloma, this is also shorter comparing to some of the Agent Orange data that's out there. So, long and short, exposure probably play a role, but there are other links: benzene, plastics, food, water, air, contaminants. What's difficult for each of us to figure is, oftentimes it's really not a one-time big dose exposure of something, right? Most of us live the normal life. We don't think about what we breathe in, what we eat routinely. It's probably harder to figure out this low-dose long-term exposure. But also to know that epigenetic changes are not limited just to the cancer cells, it's probably to the immune cell, and that's why there are many cancers that can occur. But I think my message of hope, I hope, is that changes can be reversible. You can't change the exposure in the past, but there might be something that you can actually sort of be on the lookout for the future. You know that the gut microbiome, exercise, dealing with stress, eating right, that may also affect the epigenetics, particularly of the immune system. And this epigenetic area is then becoming a new area for treatments, right? If you could actually bind or unbind the DNA in the right way to correct for the damages that has occurred in the cancer cells, it could improve treatment choices. Some cancer cells are addicted in the things that they get turned on due to this change. If you could actually eliminate that, that could help. And if I could say anything, be your own advocate. My last slide is actually a shout out to our own program. So in Indiana, we are funded by the Indiana University. We want our patients to also be the part of the journey to the cure. So we are banking patients' DNA. They give us the saliva, and if they ever get a bone marrow aspiration biopsy in the future, we ask for 5 additional cc of the bone marrow. We collect the history questionnaires, but also medical record. And very key is this exposure history, because we have this being linked to the state database. Myeloma isn't evenly distributed per population evenly all over the state. There are clusters of myeloma. We're trying to understand, are those clusters having anything unique to them? And this is really our way to hopefully be able to, in the future, answer your question better when you come to see me and ask what caused cancer. So I say we'll figure it out together. Thank you.